Well, hello everyone. Welcome back. You've been back for a while, but welcome back to statistics. This lecture is about requests, and I will take requests from you guys, but I will also take requests, in inverted commas, from what you wrote on your critical appraisal forms about what statistics was in your critical appraisals. There's some interesting stuff in some of those. However, I'm just going to show you this because it's interesting. Come on. That's too bright, isn't it? Close enough. We had chi-squared test in 10 of them, Fisher's exact test in 9, some sort of ANOVA in 9, and all sorts of interesting things. I'm really quite interested that the Klopper-Pearson confidence intervals come out 7 times. That's never happened before. So I'm going to talk about some of the things that turned up most often, and then I'll take requests. And the next time I lecture to you, it will be about writing about statistics, but that won't take up the whole lecture, and I will continue to take more requests at that time. Now, I believe that is in 2 weeks' time, and I think your presentation is like a week after that. Possibly cutting it fine, but we'll see how we go. All right. So, I've already talked about the chi-squared test, and I don't know if I talked about Fisher's exact test at the time. I can't remember, it was too long ago. So I'll just mention it again now, briefly. Okay, so the first, just warning you now that the main things I'm going to tell you about are what they're for, because that's what you need to know most. Okay, you need to know what situations they're designed to be used in, and when they're appropriate and when they're not appropriate, because that's the information you need to know for what you're doing now, and also for the future if you're analysing papers to decide if you should believe what they say. You want to know whether what they've done is appropriate. So that's what we're going to do. Fisher's exact test is designed for the same situations that the chi-squared test is designed for. So it goes like this. It's designed for this sort of situation where there's an explanatory variable that is categorical and another explanatory variable which is not explanatory, an outcome. You can tell that I've had 2 staff call in sick today and it's just been me all morning. An outcome variable which is also categorical. And the Fisher's exact test is most commonly used in the 2 explanatory and 2 in the outcome as well. So something like a treatment, placebo and treatment, and the outcome is something happening, yes or no. That's the situation in which the Fisher's exact test is used, and you may remember that that's the same situation in which the chi-squared test is used. Well, it's designed to do the same thing. So, it does the same job of the chi-squared test. It's designed to give you a p-value, because it's a test, to answer, is there a relationship? That's what it's for. I will write slower from the rest of it, because I can see that I'm not doing a very good job of clear handwriting there. That's what the Fisher's exact test is for. And the most important question at this time is, why would you do a Fisher's exact test if the chi-squared test does the same job? And the answer is, when Fisher first invented the Fisher's exact test, it's what he wanted to do. He wanted to investigate the relationship between categorical variables, and he invented his exact test to do that. And then it turned out that Fisher's exact test is actually really, really difficult to calculate by hand, mainly because it involves a whole lot of factorials and things, with calculations that are sort of big and too big for pre-computer days when Fisher was working. And so Pearson came along, and Pearson created the chi-squared test as an alternative to Fisher's exact test, and it was easier for people to calculate the chi-squared test by hand. But the chi-squared test only works if you have enough data. Okay, and if you don't have enough data in every box of your two-way table, the chi-squared test tends to give inaccurate p-values, and you can't be sure if your p-value is bigger or smaller than it ought to be. And so because you can't tell, people for a good 100 years have used Fisher's exact test instead of the chi-squared test when they have a small amount of data. So I guess the idea is that chi-squared is only accurate when there's enough data, and by enough we mean at least 5 people in every possible combination of categories. And technically you don't need to have 5 people, you just have, it's technical. Feel free to ask me about it if you're in that situation. But the Fisher's exact test is always accurate. But harder to do by hand. Basically. And so that's why the Fisher's exact test is not as common. Yes?
Why do people, I mean, most statistical analysis now is done with computer programs, so why is chi-squared relevant to Fisher's exact test?
That is an excellent question, which I was getting to, and I'm very glad that you asked it. For those on the recording or who didn't hear, why don't we always use Fisher's exact test since computers can do the calculations for us these days? Many practicing statisticians ask the same question. So Fisher's exact test is becoming more and more common. Because you can do it on a computer. And in fact, if you ask a computer to do the chi-squared test, it will almost always tell you Fisher's exact test as well on top of it, just in case that's what you really wanted. That's why it's becoming more common. But people tend to do things that they are familiar with. So when your statistics lecturer, when you learn statistics, did the chi-squared test, then so will you. And it's just continuing to people use the chi-squared test. And the chi-squared test is easier to understand because it has a test statistic, whereas the Fisher's exact test doesn't. So because t-tests are the most common kind of test ever, they have a nice test statistic and a p-value that's calculated from it with a distribution. Fisher's test doesn't have a test statistic. Not in the same way that other things do, it just gives a p-value. And so in psychology in particular, they feel uncomfortable with it. So that's just one of those things. You yourself, feel free to say you want to use Fisher's exact test. But you'll probably have to put in brackets, we could use chi-squared test, but Fisher's exact test is an exact alternative. You will have to explain why. Because of the generations of people that you're talking to may not have even heard of Fisher's exact test, even though it was invented before the chi-squared test. Because people didn't do it. Does that answer the question well enough? So yeah, that's not a maths thing, it's more of a sociology of statistics thing. There you go. So that's Fisher's exact test. And you'll find that they won't report a p-value, they won't report a test statistic, just a p-value. So, okay, next thing on the list is, all right, I am going to talk about the Mann-Whitney U-test and various other things like that, but I do want to mention confidence intervals for proportions. Okay, so for a statistician, a proportion is a percentage but written as a fraction or a decimal as opposed to as a percentage, and a ratio may be a risk ratio or an odds ratio or a hazard ratio. I'm sure there are other kinds of ratios. So they're all the same sort of thing. It's a fraction in some sense, something out of something else. And as with all statistics, you can both ask a yes or no question of is the risk ratio 1, which would mean that there's no difference in risk, or you could ask the question of is the proportion 50%, or various other stuff like that. But you could also ask the question, well, what is the risk ratio, which is what the confidence interval is for. So the confidence interval gives you a range of possibilities for what the result is. So I'm just going to repeat that, even though it's in the confidence intervals lecture. So it's a range of possibilities for the population value of the proportion or statistic. Okay, so you'll see them all over the place. You'll see your table will look something like this. It'll say like, I don't have a good example off the top of my head. Anyway, it might say, you know, age, gender, for example, and it'll have like the odds ratio, and then it'll have a confidence interval. So it might be the odds ratio is 1.3 and the confidence interval is 0.8 to 1.9, and the odds ratio here is 2.5, and it's from 1.8 to 9.7 or something. That's the sort of thing that it'll look like. Okay? And so the idea of your odds ratio or risk ratio is that for every increase of 1 in age, you're expecting a 1.3 times worse risk odds of whatever it is that you're measuring. Or for gender, when you switch from one gender to the other, you've got a 2.5 times the odds of whatever this thing is happening. But this confidence interval says that for age, it could be anywhere between a 0.8 of the original odds up to 1.9 of the original odds. And so that's saying that, well, it could be 1. 1 is a number somewhere between there. And so the odds ratio could be 1. And when a ratio is 1, it means the two things are equal. So there's no difference across age in the odds of this thing. Whereas this one doesn't include 1, and so on. And so this one doesn't include 1, and so the lowest it could possibly be is 1.8 times the odds. Yep?
Does the odds ratio have to be at the centre of the confidence interval?
No. I know that it's not in this one, is it? And so it's probably not accurate, what I've drawn there. I'm just making it up off the top of my head. But it does not have to be in the centre, and often it isn't. Often it's closer to one end than to the bottom end than the top end. So that's a worthy point, that your odds ratio doesn't have to be in the middle of the confidence interval. And that is because these confidence intervals for odds ratios are normally calculated from the logistic regression, and the logistic regression has exponentials and logs in it, and so the reason why they tend to be wider in one direction than the other is because of the exponential functions that they're doing. So the calculations of confidence intervals for things like odds ratios tend to, because of the maths that's going on, tend to be wider in one direction than the other. Okay. Oh, and also from the perspective of if it crosses 1, like 20% less is 0.8, like, well, twice as an odds, twice the risk is 2 and half the risk is a half, and they're not the same distance apart, and so that's a fraction thing as well. Anyway, what I wanted to point out is that there are multiple different ways of calculating confidence intervals. Okay, so your confidence interval could many different methodologies. Okay, it could come from, it may be that it comes from related to the hypothesis test. I can't remember the name for that one, but it may be that it's just a confidence interval for a proportion. And that's when it's not really an odds ratio, it's just an odds. It may be, or not an odds, but just a risk. It may be that it comes from a logistic regression. And often that's an odds ratio. This one's more likely to be a risk ratio. And the problem is that your standard confidence interval for a proportion is based on an assumption of having enough data and enough probability involved, and there are like all these different methods of doing confidence intervals for proportions. So there are other methods. So one of them is called Klopper-Pearson. I can't remember how most of these methods work, but one of them is Klopper-Pearson, one of them is let's look them up. See, and I can teach you important skills for reading statistics on Wikipedia. Oh crap, these are not the things I'm looking for. Right. So Wikipedia for statistics is like this. You'll have a whole lot of at the top, and then you'll go down and it'll have a whole lot of maths, because Wikipedia, the people who write Wikipedia articles for statistics are like theoretical statisticians. And so they put all the maths in. And you go, what? However, it's lucky that today all I wanted is the titles. Like, remember that for most of our purposes, it's the details of the maths are not relevant for deciding what's going on a day-to-day basis. If in some, small detailed situations where there might be a slight difference between one or the other, the maths will become an important distinction, but most of the time not. So the usual confidence interval is the normal approximation confidence interval. There's also the Wilson score interval. There's also the Jeffreys interval. There's also the Klopper-Pearson interval, the Agresti-Cooley interval, the arc-sine transformation interval, the TA transform, and all these other ones. So there are, what did we count, about 7 different methods of calculating confidence intervals for proportions. There you go. They're all possibilities. And they're reasonable for different reasons. And usually, if they've given you a name for the way they've calculated that confidence interval, the reason they've done that is they weren't comfortable with this normal approximation one. And they've done something that's a little bit more precise. So if they've mentioned they've done Klopper-Pearson, well, Klopper-Pearson is a little bit more precise. Yep. And it's also a really early one because Pearson invented it, and Pearson also invented the chi-squared test. So, yeah. So there you go. You may see Jeffreys or Wilson as well, just so you know. From your perspective, it's like, okay, that's a totally valid method of calculating confidence intervals. So tick, they've done the right thing. When I read my critical appraisal article. And you can also say, well, they've chosen to do one that's slightly more accurate than the standard one. Yeah, Jeffreys. Okay. Just so you know, I mean, this is a part of this is not really about statistics, it's about language. So what sorts of words are people using? Next, I wanted to talk about the Mann-Whitney U-test and friends. Okay, so sometimes it's called just the Mann-Whitney test, and they don't mention the U. You may also know it as the Wilcoxon rank sum test, or just the Wilcoxon test. They are 2 different methods of achieving exactly the same results. And it's just because Mann-Whitney and Wilcoxon in the same year both published them in different statistics journals at the same time, not knowing that the other had done so. And so both methods continue to be in use even though they both produce exactly the same p-values every time. Different calculations, but same p-value. And in fact, in the first year statistics course in the maths degree, called Statistical Analysis and Modelling, there's an assignment question that asks them to prove mathematically that they always produce the same p-value. Yeah, anyway. I know that because they come to my Maths Learning Centre asking me for help with that assignment question. It's very cool, but not a topic for today. And it will take me a couple of hours to remember how to do it. But what actually are they for is the main question. They are both designed as an alternative to the T-test. To the unpaired T-test. So if when you look at your research article and you think, why didn't they do the T-test? And they've done this, well, they've done it because it's an alternative to the T-test. So alternative to T-test meaning it's in this situation, categorical variable being related to changes in a numerical variable. That's what they're for. Why would you want an alternative to the T-test? The T-test has been around for, a good 100 or so years and still going strong. Why would you want one? And the reason is that the T-test, just like the chi-squared test, needs enough data to do its job properly and for its p-values to be meaningful, because you go, well, I don't know if my p-value is too big or too small because I haven't got enough data. The T-test has the same problem, but not because of the amount of data you have, but because of whether the data is normally distributed. So T-test produces accurate p-values for normal distributions. This sort of thing. That's not quite normal, but it'll do. And also under the T-test produces accurate p-values for normal distributions, and even if it's not normal, if you've got enough data, it'll be okay. And approximately accurate for large data set. Greater than 30-ish is what most people say, even if not normal. Okay. Yeah, I'd say 30 in each group. Yep, 30 in each category. But you'll find that different statisticians have different numbers for that. Anyway, so it's approximately accurate for a large data set, even if not normal. If you're doing all your statistics properly, you're supposed to check if it's normal before you do the T-test, or check that you've got enough data. Like, even if you've got enough data, you're supposed to check if it's normal before you do the T-test. Right. Well, the Mann-Whitney U-test does not require the assumption that it's normal. And that's why people use it. So if they happen to see that their data was horrifyingly skewed, they would use the Mann-Whitney U-test instead. So that's the T-test. The Mann-Whitney does not need data to be normal. And so that's why people would use it. They would use it as an alternative to the T-test in situations where they were worried about the normality of their data. So it would be okay to have something that's like that, skewed, or, horrifyingly ridiculous. These are okay. Okay for Mann-Whitney, okay for Mann-Whitney. Sweet. That's the Mann-Whitney test. The mechanism of how it works is totally different to the mechanism of how the T-test works. The T-test works by calculating means and standard deviations and doing calculations of probabilities under a T distribution. The Mann-Whitney test, yep.
Does it matter if the distribution is actually normal for Mann-Whitney?
It also works for normal distributions. In fact, there's been quite a bit of research to suggest that if your data is normal, then the Mann-Whitney U-test will almost always produce roughly the same p-value as your t-test. So one could argue that you should always do a Mann-Whitney, but again, it's one of those things. It's only been around for about 30 years. It's not in the zeitgeist yet. It works by a completely different mechanism. So the Mann-Whitney works by the philosophy that if one group is higher than the other, then you would expect the people in that group to be higher than the people in the other group. And that didn't sound like I said anything then. But basically you go through and say you count for group 2 how many of group 1 each person is above. So this person's above everyone in group 1, this person's above 20 people in group 1, this person's above 22 people in group 1. And then you add up all those scores and you do a thing. There's like some probability thing. And that's the Mann-Whitney test. And the number that you get when you add them all up is called U. The Wilcoxon rank sum test is that you actually give you lump everyone into one big group and you give them all of rank, 1, 2, 3, 4, 5, 6, 7, about what order they're in. And then you go, well, they take everyone in group 1 and add up all their ranks, and everyone in group 2 and add up all their ranks and compare those two scores of like who's higher than who. And that's where the maths comes out that they're the same in the end. So they work completely differently. So the main point is that it works on the order of the data and not on the actual values. Yep. Whereas the t-test works on the actual values. You add them all up and divide by how many there are to get the mean. And that means that when people do the Mann-Whitney U-test, they're very likely to not report means and standard deviations, but instead report medians. And that's the traditional way of doing it. So often see reporting medians and IQRs with the Mann-Whitney instead of mean and standard deviation. So just so you know, when you look at papers, sort of Mann-Whitney tends to go together with means and medians and IQRs, and sort of t-tests tend to go together with means and standard deviations. So that would be a reason why, if you've ever noticed that correspondence, if anyone's seen the Mann-Whitney, 7 pairs of you have seen the Mann-Whitney. All right, on the note of this, big note, the Mann-Whitney is what's called a nonparametric test. So, here we go. Parametric means, in literal English, means referring to parameters. And the parameters would be things like the mean and the standard deviation. A parameter is a number that describes a population. And non-parametric means not referring to parameters. So the t-test refers to the parameters. You calculate means and standard deviations. Whereas the Mann-Whitney U-test does not refer to parameters. You just stick the data in order and do some calculations on the ordering of the data. You're not specifically looking at the mean, anything that references the shape of that distribution. You're not even really looking at the median at all. You're just adding up the score, adding up the ranks. So non-parametric tests, as they're called, are often based on ordering of the data, but they generally, it's a bad word, I would prefer something else, but that's what we've got. Non-parametric tests are usually alternatives that are used when you can't use normal distributions. So usually So usually an alternative because of the non-normal distributions. That's what they usually are. That's probably a statistician, theoretical statistician would slap me and tell me that's not the correct definition, but we'll do. I should say that many psychologists and possibly other people say that the chi-squared test is a non-parametric test, and the Z test for proportions is a parametric test. That's bunkus. There's no such thing as a parametric test for categorical data. They do have parameters, but the parameter that's being referred to there is specifically the mean. So no such thing as non-parametric. All tests for categorical data are non-parametric. So just, yeah. Okay. So I'm going to make a list for you of what they're called, so what they go with. So they match with the same situation. So in the situation you'd normally do a T-test with a categorical to a numerical, that's when you do a Mann-Whitney. In the situation when you do an ANOVA, there would be something else to go with it. So let's just put some of them down. So these are things that go with normal distributions. These are things that go with non-normal distributions. So parametric, non-parametric. All right, here we go. So we've already got one, the Unpaired T-Test. And the Mann-Whitney. Or the Wilcoxon. Rank sum. Now my big document on the webpage that has that lists all these situations, what statistics goes with it, it does have under the T-test, it has a little brackets there with a little non-normal distribution symbol that says what goes with it in that context. So I'm just grouping them together here. But I only thought to do this morning when someone came to visit me to talk about their critical appraisal, and I went, whoa, this is a good idea, let's do it in the lecture today. So, all right, the unpaired T-test goes with that. The paired T-test, you can do the Wilcoxon signed ranks test. There should be the word test on all the end of these. ANOVA, ordinary ANOVA, is the Kruskall-Wallis. You'll notice the non-parametric tests are generally named after people and not by any other thing. And I just need to look something up. I'm pretty sure this is correct, but I don't see it very often. Yes, thought I was right. Okay. So if you've seen this one, repeated measures ANOVA, which I didn't really talk about but mentioned in passing, it's like repeated measures ANOVA is like the paired T-test but for multiple groups. So if you have groups that are measured in multiple different situations, individual people, in the paired T-test they're measured twice in two different situations. But if you have people measured 3 times in 3 different situations, that's repeated measures ANOVA, and the test is the Freedman test. I may have spelt Friedman wrong. Nope, that's correct. So if you've seen the Freedman test, at least one of you has. It's the situation where you have independent, where it's repeated measures more than twice on individuals. Ordinary correlation ordinary correlation, or your common or garden correlation. If people say correlation and don't specify what kind, that's the kind that we're talking about. Its official name is Pearson's correlation. And actually its proper official name is Pearson's product moment correlation. So if you ever see that, if you ever see Pearson's correlation or Pearson's product moment correlation, that's just what I call correlation. And most people, when they say correlation, that's what they mean. The non-parametric version of that is usually Spearman's correlation. All right, I think that'll do. There's the non-parametric test. So if you've seen any of those terminologies, you can just check to see if the matching situation for the ones I've told you is the right one, and then you can be pretty sure they've done the right thing. All they've done, the reason they've chosen to do those is that they're worried about the normal distribution stuff. All right. How are we doing? Okay. Finally, one last thing on my list here is maybe two more. Let's see what I can fit in. We've just finally removed the clock that wasn't working rather than fixing it. A simple solution. So tests for normality. So you know how I said with the T-test and ANOVA and regression, you're supposed to have normal distributions for the p-values to work the way they should, and especially for the confidence intervals to work the way they should. Well, there are ways of checking to see if things are normal distributions, and they are called tests for normality. And it's just good to list some of them. So if someone lists one of these things, what they're doing is they're using a statistical method for deciding whether their data is normal before they launch into their ANOVA or T-test. And there are some common ones. In fact, let us go to the internet just so that I can not miss any. Here we go. We have D'Agostino's K-squared test. Sorry, I'm going to look at the screen and I'm going to write them down for you. That's one of them. That was new to me this morning when I was helping some people. The Kolmogorov-Smirnov test. Just a second. Kolmogorov. This one's quite common. You'll see this one a lot, and some people just shorten it to the KS test. And you might also hear something called sort of a Pearson omnibus test, which is technically a combination of these two. Omnibus meaning lumping everything together. There are other tests for normality, but these are the most common. So if you do find something that feels like it, you don't know what it is. It may have near it in the text of the article that it was a test that they were testing for normal distributions, and you can go and look that up and see if it makes sense. Or it might not, but it's a fair bet that that's probably what it's for. And it's good practice to do checking, to do one of these, to check if it's normal before you do your ANOVA and various other things like that. So, before a T-test or ANOVA or regression. Yeah. So just if someone's mentioned that they've done those, they're at least trying to show that they've done everything they're supposed to do statistically. All right. Cool. Yes?
Do you do any of this stuff if you're looking at categorical?
No. So categorical variables, normality is irrelevant. Unless the explanatory variable is numerical as well. So, which is what I'm about to do. So yeah, normality only occurs for, for numerical. Unless you're in that very specific situation where technically the numerical is the explanatory variable and the categorical is the outcome variable, but you're doing a t-test on the backwards version of it as a way of checking if there's a relationship. Then you have to check normality. So it's only for numerical variables and usually only for numerical outcomes. Finally, we have, next week, 2 weeks' time, I can talk about some of the other ones. Finally, I did just want to talk about, I can talk about that next time. Anyone want to get in the last couple of minutes with a question about something? Not necessarily something I've said, but something right now while we're at it. Because I can do the other stuff for the next one. All right. Yeah? Ask away.
What is the difference between a hazard ratio and an odds ratio?
Good. That's what I was going to talk about anyway. Basically, that sort of question, like hazard, risk, or odds. Yeah. Okay. It's taken me a while to figure this out. It's the philosophy that's the difference. Let's see if I can... All right. This is time. All right, it's my timeline going from left to right. I'm sure if I was in some other countries, I would go from right to left. This is time. And when you collect information about people or do stuff to them, just collect information about people. You may collect information about people multiple times while you're watching them. You may do it before a certain event, after a certain event. You may just do it once. You may do it every week for 5 years, whatever. And that's the thing that distinguishes between these. Because if you don't know the order of events of things, and you don't know how far apart in time they are, you have less information. That's what it's about. So with odds, you only have information about what people are like now. So here we are now, and we collect information. And that's all we have. Okay? And you have information about things that are supposedly related to each other. Normally exposure to some condition, two different conditions that they might have. So eczema and asthma or whatever. And you only have the information now. Right. And in that situation, you can categorize everybody into whether they are male or female, and whether they have or have not some sort of condition, or whether they have or have not asthma and have or have not eczema, anything like that, or whether they did or did not eat the chicken, and did or did not have gastro, those sorts of things. But you don't really have information about the order in which those events happened, other than male and female, right? That's decided long before you get gastro. But it's more about not knowing when things happened. You just have information now. It might have happened here, it might have happened here. One of them might have happened before the other. So especially when it's talking about exposure, you often don't know when the exposure happened relative to the condition that you're measuring. Okay, that's odds. And what the odds represent is the chances of picking someone in one group who happens to have a condition now relative to not picking someone, like picking someone who doesn't have the condition. That's what odds is about. So odds is someone with the condition in one group relative to the other. But the key is it's picking someone. I've got a random collection of people, they already have the condition or don't, and I just say, well, in this group, the odds of picking someone here, and this group, the odds of picking someone here. You're picking people out of the group you already have. That's odds. Risk, you have time information. Risk, you have time information. Over here, back in time, you have exposed or not. You have info. And then later on, you have info now. And because you may not have been there to measure that, but someone else might have measured it. So you could still do like a retrospective cohort study. And you can do risk with that. As long as you are confident that things happened before other things, you can be sure. So if you know that the exposure to the chicken definitely happened for everyone before something, then you can talk about risk. Okay? Risk is about knowing that things are before other things. And in this case, it's not the chances of picking someone, it's the chances of someone getting to a certain spot. So, someone developing the condition. Relative to the other. And almost always in relative risk, this is risk, almost always in relative risk, everybody at that starting time point didn't have the condition, because you're wanting people to turn from not having it into having it. But in this one, we don't know whether people had it to begin with or not. Okay. And both of these, odds and risk, can be calculated from a two-way table in different ways. Hazard, on the other hand, is like even more information. So here we don't have any information about time at all. Here we have information about what happens before what. And hazard is when you know about you also know how much time there is between them. You don't just know about what happened before what, you also know that there's exactly 5 years between this event and this event. So hazard is about including how long it takes. So it's not just about the odds of it happening the chances of it happening at all, which is what risk is about. It's about the chances of it happening at any moment, given that you know how long you've been waiting for. That's what hazard is about. So hazard is of someone developing condition given a particular amount of time relative to the other group, you know. So hazard by itself is the chances, and then a hazard ratio is relative to the other group. Okay. And hazard can only be calculated using regression. You can't do it from a two-way table because you need to include the time information as well. So only... I hope that explanation helps. Let me know if it doesn't because I can make it better. Well, too late for you, but for people next year. And you can always come and talk to me in person and we'll see if we can thrash it out. Thank you so much. In a couple of weeks, I will do writing about statistics and more requests. If you have a specific request of something you want me to talk about at the lecture, email me and ask. Or alternatively, come and talk to me in person if you think that no one else cares. So, thank you very much. Good luck, and I'll see you soon.